Good morning, everybody. In today's pre-calculus lesson, we will take an in-depth look at finding zeros of a polynomial function and the end behavior of functions. More specifically, we'll cover or review, depending on your previous knowledge, the Fundamental Theorem of Algebra, Descartes Rule of Signs, the Rational Root Theorem, factoring, synthetic division, quadratic formula, and end behavior. Underneath this video, I will put timestamps regarding the various examples. So if you're comfortable with one thing, you can skip ahead to the next. Again, make this video work for you. If you're very familiar with an example, skip to the appropriate part. Okay, and without any further ado, let's look at our first example. On the screen, you're looking at the graph of f of x equals 9x cubed minus 30x squared minus 3x plus 4. So what does the graph show us? So I graphed this in Desmos and I pasted it here to the right. So we'll notice a couple of things. We'll notice that we see it cross the x-axis 3 times. So this is a root or a 0. Or an x-intercept. This is also a 0 or an x-intercept, and so is this. And I don't really know if this terminates or not. I'm going to assume that that decimal goes on and that Desmos chopped it off. And this 0.3 repeating, I'm suspicious that that is 1/3, but I'm not positive at this point, okay? But I do see those are real zeros or x-intercepts based on the graph. And the fundamental theorem of algebra states that for every non-constant single variable polynomial with complex coefficients, you're going to have at least one complex root. So what this means to you guys is if you look at the degree or the highest power, that's going to tell you how many roots you must have. So in this case, you could have all 3 could be real, which is the case here because you literally see them cross the x-axis. But if you didn't have a graph to look at, you could have 1 real and 2 imaginary, which you do not see cross the x-axis. Imaginary roots always come in pairs. So you could not have 2 reals and 1 imaginary. That will never happen. So to get to the magic number of 3 here, you could have all 3 real, which is the case here in this example, or you could have 1 real and 2 imaginary, which is not the case. If it were true, you'd only see the red line cross the x-axis once. Okay, so that tells us a little bit about what to expect, but we're going to have to dig deeper if we want to figure out how this all works. I'm going to take you guys on a little walk down memory lane. When I took pre-calculus 25 glorious years ago or so, we did not have access to Desmos. There wasn't such a thing. The internet was barely a thing at that time, and we rarely had access even to graphing calculators. So we had to do this an old school by hand way. So one way to try to figure out where the zeros are or x-intercepts was to use Descartes' Rule of Signs. So this is used to determine the number of real zeros of a polynomial function. It tells us that the number of positive real zeros in a polynomial function is the same or less than by an even number as the number of changes in the sign of the coefficients. Well, that sounds kind of confusing to me, so let's try to break it down. So if you look at the function here that's graphed to the right, look at the coefficients. We have sorry about that. I gotta get my pen going. We have a positive 9 in front of x cubed. We have a negative 30x squared. We have a negative or a minus 3x, and we have a plus 4. So those are all your signs in red. So you're looking for sign changes where it switches from positive to negative or vice versa. So if you look here, we have positive to negative. That's a change. So I'm going to write we have 1. Here we have negative to negative. That's no change. So that doesn't count. And here you have negative to positive. That's another sign change. So that's 2. So this tells us that we're going to have 2 positive real zeros, or less than that by a real number. So it could be or 0 no real positive real zeros, or 0 positive real zeros. Now, due to the luxury of technology, we can see here that we actually have 2 positive real zeros, not none. We have 0.333, that's positive, so that's this one. And we have 3.393, that's this one, okay? So that did tell us, that was confirmatory, that we have 2 positive real zeros. Okay, instead of plus here, that could be confusing. Let me write out the word positive. Now, to check for the potential number of negative real zeros, what you do is the following. You take your function and you plug in a negative x. So what's going to happen there is if you have an odd power, the sign is going to reverse. And if you have an even power on your x, the sign is going to stay the same, because a negative times a negative is positive or no change. So here we had positive 9x cubed. Since that's an odd power, 3 is odd, we're going to flip the sign to negative 9x cubed. Next we have minus 30x squared. Since that's an even power, we're going to leave it alone, minus 30x squared. Next we have minus 3x. Remember, that's x to the first power. So since 1 is odd, we're going to flip that sign. So instead of minus 3x, it's going to become plus 3x. And then finally, we're going to write down our constant, which was a positive 4. So that's positive 4. Now let's look for sign changes starting from left to right. So we have a negative and a negative. That's no sign change. Now we have a negative to a positive. That is a sign change. So that's 1 sign change. And now we have a positive to a positive, which is not a sign change. So that means that we have 1 negative real 0. And since we have this technology, it's right here, okay? It's this one, negative 0.393. So Descartes' rule of signs can be informative. It doesn't find the zeros for you, but it can give you an idea what to look for or what to expect. This is an old school way of doing things. Even more informative than Descartes' rule of signs would be something called the rational root theorem. So the rational root theorem says, given a polynomial, there is a process we can follow to find all of its possible rational roots. Remember, a rational number can be written as a fraction. It is a terminating decimal. It does not go on forever. So it's not something goofy like the square root of 3 or the square root of 7. It's a fraction, and if it's a decimal, it terminates or stops. And this process is defined within the rational root theorem, which states all the possible rational roots of a polynomial can be represented as P over Q, such that P over Q equals factors of the constant divided by factors of the leading coefficient. Okay, let me break this down for you guys. So we call P factors of the constant. The constant in this example is the number at the end, the positive 4. So if I get out my pen, we have this positive 4, that's the P value. And Q is the factors of the leading coefficient. So the leading coefficient here is this 9. The 9 is going to be the Q. So we have to say that P over Q would be 4 over 9, but it's not literally 4 over 9. It's the factors. So what times what gives you 4 and what times what gives you 9? Well, let's break down 4. 4 would be 1 times 4, or you could have 2 times 2, okay? So I'll separate those with commas, 1, 2, and 4, over the factors of 9. You could have 1 times 9 will get you 9, or you could have 3 times itself. There's no point writing 3 more than once. So the factors of 4 are 1, 2, and 4. The factors of 9 are 1, 3, and 9. So what this will do is this will tell you not confirmatory, but possible zeros or roots of the function. So how it works is this. You can take any number from the numerator here and divide it or write it as a fraction with any number over the denominator. So for example, we could have 1 over 1, which is 1. We could have 1 over 3, which would be 1/3. We could have 1 over 9, which would be 1/9. We could have 2 over 1, so I'm right here. 2 divided by 1 would be 2. We could have 2 over 3, which would be 2/3. We could have 2 over 9, which would be 2/9. We could have 4 over 1, which would be 4. We could have 4 over 3, which would be 4/3. And we could have 4 over 9, which would be 4/9. Okay, I think that is every combination of numerator over denominator. So what this means is this is possibilities for the zeros or the x-intercepts of this function. Now, where this is helpful is I would say that this 1/3 pretty much confirms that this is indeed 0.3 repeating. I would say with very little doubt, this has got to be 1/3 because this rational root theorem confirms that. Now, if you were to change these in decimals, and I'd encourage you to do so, not one of these is 0.393 negative or 3.393. So that means the only one that is a rational number is this 1/3, okay, which is 0.3 repeating. So these two are not rational, and this method won't give you those. Also, to confound things, each one of these could be positive or negative, okay? So basically what this is telling you is there are 18 different possibilities for roots here if you do not have the graph to look at due to new technology, okay? So if I were asked 25 years ago, 30 years ago to find all of the zeros of this function, I would have to have done the following. I would have to have taken all 18 of those values, okay? Now I have all the positive ones lined up on the left side of the screen, and I have all the negative ones on the right side of the screen. So for all my x values, right, I'd have to plug in for x here, here, and here. So in this one, I plugged in a 1/9. In this one, I plugged in 2/9, 1/3, 4/9. And you're looking for zeros of the function where f of x is equal to 0. And you can see all my results here. As a student, I would have had to literally have done this 18 times. And the only one that yields a 0 is 1/3, okay? So this is an awful lot of work when you could have just looked at the graph. So we're gonna work smarter than, rather than harder, and we're gonna use Desmos. So what I'm saying to you, instead of doing all this guess and check work, another way to do this is you could do synthetic division and look for a remainder of 0, but this is far too much. This is 2020, this is not 1995. So I'm going to show you moving forward how to avoid doing all this, and we will work smarter instead of harder. So going back to our example here, I would suggest you do the following. Put this in the Desmos and look for something that seems to make sense, okay? 0.333 indicates 1/3. We did confirm that using the rational root theorem, but going forward, I don't think we have to go through all that work. So what we're going to do is we're going to take this 1/3 and we're going to use synthetic division. So we're going to divide by this 1/3 here. And what I like to do is put it in a little bracket. And then I write down the coefficients of the polynomial. The coefficients are just the number part. So in front of the x cubed, I have a 9. Leave a little space. I have a minus 30. I have a minus 3. And I have a positive 4. Now I draw what I call my answer line and my remainder line. If I were to have a remainder, it would be right here. I need a remainder of 0. If I don't get a remainder of 0, it means two things. It means you either did not divide by a 0 of the function, or you made an arithmetic mistake somewhere. So carrying on, this is how you do the synthetic division. You take your leading coefficient, which is 9, and you drop it down into your answer line. Now, when you're in your answer line, the only thing you may do is multiply back to the divisor here, that 0 you found off the graph. So a third of 9, or 9 times 1/3, that's like dividing by 3. A third of 9 is 3, so that goes here. When you're in this column, the only thing you may do is get the sum. So a negative 30 combined with a positive 3 is negative 27. When you're in this answer line, the only thing you may do is multiply back to the divisor, which we got off of Desmos as a 0. So negative 27 times a third, which is a third of negative 27, is negative 9. Now that you're in this column, you have to get the sum. A negative 3 combined with a negative 9 is a negative 12. Okay, last time, multiply back. Negative 12 times a third is a third of negative 12, which is negative 4. And 4 minus 4, 0 out, which is perfect. Okay? So now what's happened is, since we divided 1/3, your polynomial drops down from a cubic third power to a second power degree, and these are all the coefficients. So we have 9x squared minus 27x and then minus 12. Okay, so this is the quadratic equation we're left with, and we can try to factor it or use the quadratic formula. Now, I'm not even going to bother trying to factor this because I know the quadratic formula works every time, so I'm just going to elect to do that. All right, so now we're going to work out the quadratic formula so we can find the remaining two zeros. Okay, that's what it will do for us. So I'm going to take this, and my 9 is my A value. Sorry about that. My 9 is my A value. Negative 27 is my B, and negative 12 is my C. So I'm going to plug it in. X equals, right here we're at the opposite of B. So the opposite of negative 27 is positive 27, plus or minus a big old radical square root, B squared, which would be negative 27 squared, minus 4 times the A term, which is 9, times the C term, which is negative 12, all over 2 times A again being 9. All right, so the next step here will be to crunch this out a little bit more. So we have X equals 27 plus or minus the square root. I'm going to punch this all into my calculator in parentheses, just like you see it. So parentheses negative 27 squared minus 4 times 9 times negative 12. That will give me 1,161, or 1161. So that goes in the radical all over 2 times 9, which is 18. All right, so let's keep going. We have X equals 27 plus or minus. Let's see what happens if we take the square root of 1161. So the square root of 1161 is, that looks like it's irrational. It's 37.0734. So for now, I'm just going to leave it as it is, okay, over 18. So now I'm going to do the two cases to get approximations for these roots. I'm going to do 27 plus the square root of 1161, enter, divided by 18. That gives me approximately 3.392 2, 9, etc. It keeps going on. And then to get the other one, I'm going to do 27 minus the square root of 1161 divided by 18. And I'm going to get negative 0.3929. So you can see that this would be the exact answer here. But to get a feel for where they're coming from on the graph, these are the approximate values. So this one here is this guy, Desmos rounded it off, and this one here is this guy. So they're real solutions because you see them cross the x-axis, but they're irrational. They repeat in no particular pattern. I mean, not repeat, they go on in no particular pattern forever, okay? So you have, they're all real, all three are real. So 2 of them are irrational, and then this 1/3 is rational. So those are your 3 zeros or roots of this equation. Okay, so this is what I'm suggesting to do. Use Desmos to find the clearest one possible, the one that looks like rational, which would be either a fraction or a whole number, integer, and then use synthetic division, and then do factoring or most likely quadratic formula. Okay, next is a you try. I want you guys out there in YouTube land to try x cubed minus 10x squared plus 15x plus 2. The objective is to find all 3 zeros. You have to get 3 because that's the degree. So I want you to pop this into Desmos, find a clear 0 or x-intercept, and then get to dividing with synthetic division. So now would be a great time to hit that pause button and try it yourself and then resume, and then you can see the answer. If you need to see the work, watch it. If you just want to fast forward to the answer, that's great too. Make it work for you. So at this point, hit pause, give it a try, and then unpause when you'd like to see my solution. Okay, so now you can see a little clip from Desmos. So you can see that you have a couple of decimal-based zeros, and you have this one here that is at 2. Okay, so that is a nice clean number. So we're going to use this 2 here to divide using our synthetic division, okay? We have no reason to believe that these decimals terminate or stop. They're probably irrational. They most likely go on forever, and they're the end product of some kind of a square root. So we'll see. So grab this clear 0 or x-intercept of 2, and we're going to put that in a little bracket and do synthetic division. So now we write down our coefficients. This was a 1, so we have 1, -10, 15, and 2, answer line and remainder line. Bring down your leading coefficient, 1, underneath the answer line and multiply back. 1 times 2 is 2. Get your sum in the column. -10 plus 2 is -8. Multiply back. -8 times 2 is -16. Get your sum. 15 take away 16, you're in the hole by 1, -1. Multiply back. -1 times 2 is -2. Get your total here, your sum. 2 minus 2 is 0, which is what you needed. You needed no remainder. If you got a remainder, you either made an arithmetic mistake or you did not get the correct 0 off of the graph. So at this point, we have, this means 1x squared minus 8x minus 1. So we are ready to do the quadratic formula to find the remaining 2 zeros, which we will do right now. Okay, so with the quadratic function x squared minus 8x minus 1, this 1 here is our a, -8 is our b, and -1 is our c. So if we do the quadratic formula, x equals -b, or the opposite of b. Since we had a -8, the opposite of that is +8, plus or minus square root b squared, which would be -8 squared, minus 4 times the a, which in this case was 1, times the c, which in this case was -1, all over 2 times a being 1. Okay, so now I'm going to do my rewrite. X equals 8 plus or minus square root. So we've got -8 squared is 64 Then we have minus 4 times 1 times -1 is a -4. All over 2 times 1 is 2. Do another rewrite. We have x equals 8 plus or minus the square root of 64 plus a negative. I'm sorry, 64 minus a negative changes to plus. So we have 64 plus 4 is 68 all over 2. So at this point, we can try to break down the 68, see if it's divisible by a perfect square number like 4, 16, 36, etc. It turns out that it is divisible by 4. All right, so we will say we have 8 plus or minus, since 68 is divisible by 4, we're going to say it's root 4 times root 17, because 4 times 17 gets you back to 68. 4 being the perfect square, all over 2. So now I'm going to do another rewrite. I have 8 plus or minus. The square root of 4 is an exact 2. The square root of 17 doesn't break down. And then I have all of that over 2. So now, finally, we're going to divide out this 2 in the denominator. 2 goes into 8 4 times. 2 goes into exactly once, so we're left with the root 17. So there are 2 of our real but irrational zeros or roots, 4 plus or minus root 17, and then the one that we got off of Desmos first was 2. Okay, so these are our 3 zeros of the function. So what I would do to confirm to make sure I got it right is, I know this 2 is correct because I got it from right there, but let's see what this 4 plus or minus root 17 means. So in my calculator in my hand, I'm going to press 4 plus the square root of 17. I get 8.123, which is this one right here. Okay, and then I'm also going to press 4 minus root 17. 4 minus root 17 is negative 0.123, which is this one right here. So these are approximate values. This here is the exact value. So now we have found all 3 zeros. Again, Desmos only gives you approximations. By doing the hard math by hand, you actually can get an exact value like the following. Okay, so there you go. There's a couple examples of finding all of the zeros of a cubic or third power polynomial. Now we'll move on to how do you deal with a fourth power polynomial. Let's check it out. Okay, so in our next example on the screen, you see the graph of f of x equals x to the fourth plus 3x cubed plus 8x plus 24. I popped that into Desmos and put a screenshot here so we can see that it clearly crosses the x-axis at -3, and it also clearly crosses the x-axis at -2. I do not see it cross the x-axis anywhere else, so that implies to me that we have 2 real zeros or x-intercepts, and we also have 2 imaginary ones because we do not see that cross anywhere. You have to get to the magic number of 4, which is your degree or highest power of the function. So it looks like we're dealing here with 2 real and 2 imaginary. So we can start by using the -3 or the -2. It doesn't matter which. I'm just going to say let's go with -3. We'll put that in a little bracket and we'll do synthetic division. So our coefficients of this polynomial here are 1, 3. Ooh, hold on, pump the brakes. It has to go in a descending order. So this is fourth power, third power. Where in the Sam Hill is the second power? It's not accounted for here, so we have to put in a placeholder 0. It's very important. So fourth power coefficient, third power coefficient, second power coefficient, we don't have any. And then our linear power is 8 and our constant is 24. Okay, very important here to see that there is that gap. So now we can rock and roll. Answer line, remainder line. Drop down your leading coefficient, multiply back. 1 times -3 is -3. get a total. 3 minus 3, 0, no problem. 0 times negative 3, 0, get your total or sum. 0 plus 0 is 0. Multiply back. 0 times negative 3, 0. Sum. 8 plus 0, 8. Multiply back. 8 times negative 3 is negative 24. And we indeed have a remainder of 0, which is perfect. Okay? So now, what we are working with is we have to do synthetic division again. All right? So now what we're going to do is we're going to take the other 0 off the graph. We just used the negative 3. So now we're going to grab the negative 2. So we're going to have negative 2. And then I'm going to recopy down these coefficients. You do not use the remainder. So we're going to have our 1, 0, 0, 8, answer line, remainder line. Pull down this leading 1. Multiply back. 1 times negative 2, negative 2. Get a sum. 0 take away 2, negative 2. Multiply back. Negative 2 times negative 2, positive 4. Get your sum. 0 plus 4, 4. 4 times negative 2, negative 8. And mercifully, 8 and minus 8, 0 out. No remainder. Perfect. So now this is your A, B, C. We have 1x squared minus 2x plus 4. We are ready to do the quadratic formula and see what's going on, and we can expect 2 imaginary values because we already got the real ones. That's all we could see off the graph. So without further ado, let's use the quadratic formula on x squared minus 2x plus 4 and cook this son of a gun. All right, so quadratic formula time. X equals negative b. Boy, all of these b's have been negative to start with. That's minus 2. So the opposite of that is positive 2, plus or minus the square root of b squared. So that's negative 2 squared minus 4 times the a value, which is 1, times the c value, which is 4, all over 2 times a was 1. Okay, do a rewrite. X equals 2 plus or minus. What do we got inside the square root here, folks? We got negative 2 squared is positive 4 minus 4 times 1 times 4. 4 times 1 is 4 times this other 4 is 16. All over 2 times 1 is 2. So you might see what's happening here. We've got 2 plus or minus the square root of 4 minus 16. We're taking away a bigger from a smaller, so we're into the negatives. 4 take away 16 is negative 12. So there is our problem. That's why they're imaginary. Okay, do another rewrite here. So we'd have x equals 2 plus or minus. So let's see here. Does 12, root 12, does this contain a perfect square? 4, 9, 16? Yep. It's divisible by 4. So I'm going to split up negative 12 as root negative 4 times root 3, because negative 4 times 3 gets us back to negative 12, all over 2. If I simplify it again, I've got 2 plus or minus the square root of negative 4 is 2i, because the square root of the negative 1 part of that is I, and the square root of 4 is 2. I tack on my square root of 3 because square root of 3 doesn't break down, doesn't contain a perfect square. Divided by 2. And last step is to divide out this 2 in the denominator. 2 goes into this 2 once, plus or minus. 2 goes into this 2 once. So I just have I root 3. So in an overview, the zeros of this function are the negative 3 we got off of Desmos, the negative 2 we got off of Desmos, and then the imaginary ones come in pairs. We have 1 plus I root 3, comma, 1 minus I root 3. That is all 4 of them. Remember, 4 was the magic number because that was the degree of the polynomial. So that is an example using a 4th power polynomial where you end up with 2 real and 2 imaginary roots. All right, next up is a you guys try one and see how you can do. All right, so here's one for you guys again in YouTube land to try. See if you can find all 4 zeros of this polynomial. Okay, so there's going to have to be 4 zeros. They could be a combination of real and imaginary. Let's see what happens. So pop it into Desmos, find a clear, nice, friendly 0 off of there and start synthetic dividing. Hit pause, and when you are ready, unpause, and you can see how you did. Okay, so if you're ready to watch the solution, here we go. When I plugged this into Desmos, I saw a 0 at -2, and I saw one at 4. So that would imply to me that we probably have, or definitely have, I guess, 2 real zeros and 2 imaginary, which we don't see. So you can start with either one. I'm going to start with the 4. So I'm going to take this 4 and I'm going to do synthetic division. Let's grab our coefficients. So we have a 1, a 2, 4, 3. Okay, what happened to our second power? It's not there, so you have to put in a placeholder 0. And now we have -64 and -28. Keeping in mind your placeholders, any power here could be missing. It's just a coincidence. We had, I think, the second power missing twice, so just be aware of that. Answer line, remainder line, bring down this leading coefficient, multiply back. 1 times 4 is 4. Get your sum here. 2 plus 4 is 6. Multiply back. 6 times 4 is 24. Get your sum. 0 plus 24 is 24. Multiply back. 24 times 4 is 96. All right, so let's see. -64 plus 96 would be, is that 32? And then 32 times 4 is positive 128. And with a little bit of luck, those indeed cancel, which is what we needed. Okay, so now what we're going to do is we are going to divide by the other clear, nice, friendly, rational, real 0 we saw off of Desmos, which was this -2. So I'm just going to put that right here, put my little bracket, and I'm just going to go to town. Bring down this 1. 1 times -2, -2, get our sum. 6 take away 2 is 4. 4 times -2, -8. 24 minus 8, 16. 16 times -2 is -32, and that was our remainder of 0. So now this is our A, B, and C. So we've got 1x squared plus 4x plus 16. Does not appear to me that can be factored because I don't think there's anything that multiplies to 16 that also sums to 4. So again, we are back to the quadratic formula. Okay, so let's hit the quadratic formula. X equals -b. B this time was +4, so we go with -4 plus or minus the square root b squared, so that would be 4 squared minus 4 times the a value, which is 1, times the c value, which is 16, all over 2 times a being 1. Do a rewrite. X equals -4 plus or minus the square root. Let's see, 4 squared is 16 minus 4 times 1 times 16 is 64. All over 2 times 1 is 2. Do another rewrite. -4 plus or minus the square root. 16 take away 64. I'm getting a little bit tired here, so make sure I don't make a mistake. -48. All over 2. So now let's see if we can break down this square root of 48. It is not a perfect square. If you take the square root of 48, you get a decimal, but does it contain a perfect square? Is it divisible by 4, 9, 16, 25, 36, etc.? It turns out that it is divisible by 16. 16 goes into 48 3 times. So when I do my rewrite over here, I've got -4 plus or minus. I'm going to say it's the square root of -16 times the square root of 3, because this one here is a perfect square, and negative 16 times 3 gets you back to 48, all over 2. If we do another rewrite, we've got negative 4 plus or minus the square root of 16, negative 16. The square root of 16 is 4, and the negative gives us the imaginary unit. We have to tack along the root 3 because that doesn't break down, all over 2. So then last steps here would be to divide out the 2 in the denominator. 2 goes into negative 4, negative 2 times, plus or minus. 2 goes into this 4 twice, so I have 2i root 3. So these are my imaginary solutions. These are my real solutions. So in summary, my 4 zeros of this function would be negative 2, positive 4, negative 2 plus 2i root 3. You don't see that because of the imaginary unit. And negative 2 minus 2i root 3. So there they are, ladies and gentlemen. 1, 2, 3, 4. Okay, I hope this helps. There's a lot of reviewing here, how to break down radicals, quadratic formulas, synthetic division, all that good stuff, but that is my process and I'm sticking to it. So this wraps up our review of finding roots or zeros of polynomial function. The remainder of this video is a quick look at the end behavior of a function, and we'll get this one in the books and wrap it up. So, end behavior, if you've never studied it before, refers to what is happening to the extreme left and the extreme right of the domain of a graph. So let's look at a couple of different cases here. If you look at an even degree polynomial, like a graph of x squared or a graph of x to the 4th, something like that, okay, where the highest power is even, like 2 or 4, what happens here is the following. If you look all the way to the left, it goes up to positive infinity, okay? Same thing. So if you have an even degree and you start out with a positive, it's positive x squared, positive x to the 4th, you can say the following. As x approaches negative infinity, which means to look to the left, what happens to your graph? It goes higher and higher and higher forever to positive infinity. So you say the function value or the height approaches positive infinity. Then you can also say as x approaches positive infinity, which means to the right, as you move to the right on either this graph or this graph, you go higher and higher and higher forever, which means that all function values approach positive infinity, okay? So if you have an even degree polynomial with a positive leading coefficient, which means that this could be 3x squared, it could be 7x squared, it's just the power is even, 2, 4, 6, 8. If these are positive, they're both going to go up and reach positive infinity, okay? So that is the even degree positive leading coefficient case. Okay, next you have the case of still even degree. So it's x squared or maybe x to the 6th, but it's a negative leading coefficient, all right? So maybe like a negative 5 or a negative 2, or just plain old like negative x to the 4th, all right? So an even power, but a negative lead-off coefficient. You'll notice that these point down from the left of the domain all the way to the right, they end down. So it will say as the following: as x approaches negative infinity, which means you go towards the left, they go down forever, which means that the function values f of x approach negative infinity, they're going down forever. Also, as x approaches positive infinity, means you're moving to the right in the domain. As you go to the right, it's also pitching down. So that means that f of x also approaches negative infinity. So this is the case for an even degree polynomial with a negative leading coefficient. It makes both left and right side go down to negative infinity, okay? So next we will look at not an even degree, but an odd degree, like 3rd power, 5th power, etc. All right, so let's take a look at an example of odd degree. So you might have x to the power of 3 being odd, or maybe you have something like 6x to the power of 5 being odd. Again, you're not looking at the coefficient, you're looking at the power, and these are positive, okay? It's positive, positive. So what's going to happen here is as x approaches negative infinity, which means you're looking towards the left, follow your graph to the left, it's going to pitch down. Follow this one to the left, it pitches down. So that means your function values approach negative infinity. But as x approaches positive infinity, meaning that you're looking to the right, as you move to the right, it goes up forever. As you move to the right, it goes up forever. So you're going to say that f of x approaches positive infinity. So these odd ones are split. The left side goes down. So as x approaches negative infinity or left, the function goes down. But as x approaches positive infinity, which means to the right, the height of the graph goes up. Okay? So these odds are split. They're not double up, double down like the evens. They're 1 and 1. Okay? So then finally, what happens if you add in a negative for the leading coefficient? Well, it's a reflection. They flip upside down. So we will look at that as our final case. All right, so if you have a leading coefficient that is negative, and we're still talking about odd degree polynomials. So maybe this is like negative x to the third, and maybe this is like negative 2x to the seventh or something crazy like that. Notice now that the left side goes up and the right side goes down. The left side goes up and the right side goes down. So you're going to say that as x approaches negative infinity, or you're looking left, what happens? On the left side of the graph, you go up forever. The left side of the graph goes up infinitely. So that means the function values approach positive infinity. And as x approaches infinity, which means look to the right, so to the right, as you move to the right, it ultimately pitches down. As you move to the right, it ultimately pitches down. So that means the function values approach negative infinity. So this is how you write up end behavior. And these are the rules, and we're sticking to them. You can see them on the graph. So hopefully this helps if you guys are asked to describe end behavior. So hopefully you learned or refined your skills in zeros of polynomials and a little intro to end behavior. Thank you so much for watching this HansenMath YouTube video, and good luck to everybody in your studies, and have a wonderful day.